All right, definition of a function. A relation is said to be a function if and only if each x value corresponds to only one y value. Graphically, we can use the vertical line test to determine if the graph is a function. All right, so let's look at the following graphs and see what I'm talking about here. So a vertical line test means we're going to take an actual vertical line, and we're just, imagine we have an infinite number of these things, and we're going to look and see how many times does it actually cross a vertical line. And so here I can see it once and once and once. And no matter where I draw the vertical line, it's only going to cross it one time in this first particular picture. So we would say that it passes the vertical line test and that it is in fact a function. Okay, in this next example, you can see several places where we can draw a vertical line, and it's going to cross more than once. So we say out loud that it fails the vertical line test and it is not a function. All right, in this last example, so again I'm going to draw a couple of vertical lines and convince myself that either it passes or it doesn't. And you can see very easily that it's only going to cross the line once. So this in fact is a function. Okay, so a special case of a function is what's called a one-to-one function. So a one-to-one function is said to be one-to-one if each y value corresponds to only one value for x. In other words, a function is if x corresponds to y. If it's one-to-one, then y corresponds to x. Just kind of partner up back and forth. Graphically, we use what's called the horizontal line test. To determine if a function is one-to-one. Okay, so again, we're assuming it is already a function. Now we're throwing the more specific name one-to-one on top of it. So horizontal line test, just like it sounds. I'm going to draw horizontal lines and see if there's any place where it crosses more than once. So I can see numerous times it does that. So this is not one-to-one, even though it is a function. Okay, next example, again, horizontal lines. And I can see no matter how I draw a horizontal line, it's going to only touch once. So this is in fact a one-to-one function. And our last case here, and again, same logic, no matter how I draw a horizontal line, it's only going to cross once. So it is in fact a one-to-one function. Alright, so that brings us to an idea of what's called an inverse. And in order for an inverse to even exist, we are assuming that we are dealing with a one-to-one function. And let me kind of paint a picture as to why that is. So let me start with just a couple of numbers. So I'm going to partner up 1, 2, and 3 with the numbers 4, 5, and 6. And of course, to be a function, it's got to be it's got to partner up each x with a unique y. So I'll partner up 1 with 4, 2 with 5, and 3 with 6. And of course, that's our input right there. And that's our output of whatever this particular function does. Okay. So looking at our ordered pairs then, is f a function? Well, yeah, each x value is only partnered with one y value, so that's a yes. Is it one-to-one? Okay, one-to-one is, look at the other direction. If I look at 1 to 4, can I partner up, is each y value partnered up with only one x value? And the answer to that one is yes. Okay. Now, with an inverse, what I'm going to do is I'm going to switch domains and ranges. So I'm going to take the domain of f, and I'm going to swap it out with the range of g, and I'm going to take the range of f and swap it in for the domain of g. Okay, and so literally what am I saying? I'm saying that I'm going to go into this g function, and I'm going to write, so I can scroll down here, 4, 5, and 6 for domain, and 1, 2, and 3 for inverses, and then I'm going to partner them up accordingly. So 4 goes with 1, 5 goes with 2, 6 goes with 3. And notice I've just switched the order of the two inputs and outputs. So the input of f is the output of g, and the output of f is the input of g. Okay, now let's look at g by itself for just a second. Is g considered to be a function? And we can see that each x is partnered up with a unique y, so that's a yes. Is g 1 to 1? Well, there's only one is partnered with, the y values are partnered with a unique x value, so we can kind of go backwards there. So that is also a yes. Okay, and so the relationship between f and g, that's where this inverse idea comes in. That we're just reversing the order, so we're undoing whatever the original function did, and that's what we consider to be an inverse. Okay, so still kind of hanging out with this function f and g that we've been playing around with, of the 1, 2, 3, and the 4, 5, 6. Just want to visually try to explain again what's happening here. So I'm going to take 1 and I put that into f, and what does f produce for us? So I'll come up here, and 1 is partnered with 4, so I get a 4 out. Input versus output. Now, what happens with g? So g, if I take a 4 and I put it in g, what will we expect the output to be? We would expect that to be a 1. Okay, so in using composition notation then, what I'm saying is that if I take g of f of 1, that I should end up back with the original input. Okay, let's kind of do another example. So let's say I take the number 2 and I put it inside our function machine. What number would I expect to come out? So what was partnered with 2? That was 5. So if I take 5 and I input it inside the g function, what was partnered with 5? That would be 2. And so g of f of 2, I would expect to be the original input. Okay, so in general sense then, if I take an x and I work out the function, I should get out f of x. And if I take that, and that's now my input, and I put that inside of g, what would I expect to get out? I would expect to get an x out. So g of f of x should simplify down to x. Okay, similarly, kind of go backwards here. Let's say I take a 6 and I put it inside g. What number would I expect g to give me? In other words, what was partnered up with 6? That was 3. And so if I put 3 inside of f, I should get a 6 out again. So f of g of 6 was the original number that we started off with. So we hopefully we're sort of getting the stronger sense as to that this f and g that we're describing, that they undo each other with their opposite operations.